Resistors are one of the most fundamental electrical components. Pretty much every circuit that does something useful requires resistors to do some kind of work. In this video, I'm going to do my best not just explain the theory behind resistors, but also show some practical examples of how they're actually used in circuits. I want this to contain the kind of information that would have been helpful for me when I was first getting interested in electronics. So let's get started. A resistor is an electrical component that, as you could probably guess, resists the flow of electricity. More specifically than that, as electricity flows through a resistor, some portion of that electricity is converted into heat. This conversion into heat is what actually reduces the current. The more electricity flowing, the more heat is generated. The more resistance of the resistor, the larger the portion of current is lost to heat. Resistors are generally rated based on two main properties: how much resistance they offer, which is measured in ohms, and how many watts they are rated to withstand, which tells you how much electricity the resistor can handle before it actually gets so hot that it burns up and destroys itself. But how are resistors actually used in circuits? Let's go over some very basic examples to show how resistors affect the voltage and current in a circuit. In order to understand the effect resistors have, it's very important that we understand Ohm's law. Ohm's law gives us the relationship between voltage, amperage, and resistance. That relationship being V equals I times R, or voltage equals current times resistance. Using this formula, we can predict what will happen in a given circuit if we change any of these three properties. The simplest circuit we can put together is a voltage source and a single resistor. I'm going to use a 5 volt DC voltage source and a 1 kilo ohm resistor. Using Ohm's law, we can calculate that we should have about 0.005 amps, or 5 milliamps of current passing through our resistor. 5 milliamps times 5 volts equals 0.025 watts. Wattage is just the voltage and current multiplied together. These cheap resistors are rated for a quarter watt, so this is well within what they can handle. If I swap out the 1 kilo ohm resistor for a 2 kilo ohm, our new current will be 2.5 milliamps, half of what it was before. So we can clearly see that the relationships between voltage, current, and resistance are linear. If we double the resistance, the current will halve. If we halve the resistance, the current will double, and so on. Something I should quickly mention about these carbon film resistors is that these colored bands represent the resistance rating of the resistor. You can absolutely use this system to read what resistance a resistor is rated for, but if you have a multimeter, and you should get one if you don't, I find it way easier to just set my meter to measure resistance and check their value that way. When you experiment with circuits, you will just end up with piles of resistors of different values that you've used, and you absolutely should double check their value before you organize them and put them away. One of the main reasons that we would want to include a resistor in a circuit is to limit the amount of current going through a sensitive component. For instance, an LED emits light when electricity passes through it, but if you allow too much current to pass through it, it will destroy itself. So, using our 5 volt source, we can use Ohm's law to calculate how big of a resistor we would need if we wanted to ensure that only about 20 milliamps would pass through the LED. We need about 250 ohms of resistance. I don't have an exactly 250 ohm resistor, so I'll use this 270 ohm one instead. Putting in a 270 ohm resistor, our LED lights up, and we can be assured that it isn't going to blow itself up in the process. Let's make our circuit a little more complicated. Suppose instead of just one resistor, we had two. The resistance of these behave differently depending on whether we connect them in series, end-to-end, or in parallel, side by side. The behavior of resistors in series is easy. Their resistances just add together. If we have a 2 kilo ohm resistor and a 500 ohm resistor in series with each other, the resistance of the circuit will be the same as if there was a single 2500 ohm resistor in their place. Things get more interesting though when we look into the voltage and current of a circuit with more than one resistor. I'm going to talk about the voltage first, and this can get confusing if you don't understand what we are really measuring when we talk about voltage. Unlike resistance and current, voltage measurements are a measurement of the difference in electrical pressure between 2 points in a circuit. The measurement you get will be different based on what 2 points you choose to measure from. It's not enough to simply say that a circuit has 5 volts of electrical pressure. You have to specify that it has 5 volts of pressure relative to another specific point in the circuit. When two resistors are in series like we have here, the voltage across both resistors will be equal to our supply voltage, which is 5 volts. However, the voltage will be divided between them, meaning if we measure across each resistor's leads individually, we'll get two different voltages that add up to 5 volts. Likewise, if we use two 1000 ohm resistors, they will each still have 2.5 volts across their leads. The voltage remains the same in these two scenarios, but the two 1000 ohm resistors will have a lower current passing through them. If R1 is 500 ohms and R2 is 1000, we will see 1/3 of our supply voltage over R1 and 2/3 over R2. The voltage is divided proportionally between the two resistance values. When it comes to current in resistors in series, the current at all points in the circuit will be the same. To calculate the current in our whole series circuit, we just add our resistor values together and treat them like one big resistor and use Ohm's law. Using resistors in series, we can create a very important electrical circuit called a voltage divider. If we have a DC circuit with a set voltage, and we want to reduce that voltage by a certain amount for a particular component, we can use a couple of resistors in series to accomplish this. Suppose we have a 9-volt battery, and we want to power an LED that requires 5 volts. 9 volts will overwhelm and damage the LED, so we need to reduce the supply voltage by 9/5. We can do so by putting two resistors in series, where R2 is 5/9 of R1 plus R2. I'll choose 270 ohms for R1 and 330 ohms for R2. Now, if we put an LED in parallel with R2, it will effectively have 5 volts across its leads, and the R1 resistor will be limiting the amount of current passing through the LED to a safe level like we did before. Voltage dividers are genuinely useful in electronics. They are not uncommon to find uses for. Resistors in parallel behave a bit differently. If you think about it, when you put multiple resistors in parallel with each other, you are providing additional paths for electricity to flow. So, it would logically make sense that as you provide more paths for current, the amount of current flowing would increase. And if current is increasing, while voltage is staying the same, then the resistance must be decreasing. And this is exactly what happens. When two or more resistors are in parallel, their combined resistance is equal to the inverse of the sum of all of their inverses. And there are two cases where a simpler formula can be used. When you have exactly two resistors in parallel, or when all of the resistors have the same value. When you have just two resistors, their resistance is equal to their product divided by their sum. And when you have two or more resistors that all have the same value, their resistance is equal to their value divided by how many of them there are. An interesting consequence of this is that the combined resistance of resistors in parallel is always less than the smallest resistor present. You can think of the behavior of voltage and current when resistors are in parallel as being opposite of how they behave in series. In series, the voltage is proportionally divided among the resistors, and the current is the same at all points. But when in parallel, the voltage is the same across each resistor, and the total current is proportionally divided among them. When would you want to use resistors in parallel? Well, you would do this when you want to control how much current is going to different parts of the circuit rather than how much voltage is. So, if you wanted to design a circuit with 3 paths for current, where the first 2 paths each have 10 milliamps passing through them, and the third path has 20 milliamps, you need to choose resistance values where the total resistance allows for 40 milliamps of current, the first 2 resistors are of equal value, and the third resistor is half the resistance of the other 2. Using Ohm's law, this really isn't as hard as it seems. If you understand the fundamental behavior of voltage and current when resistors are in parallel or series, the math itself is pretty simple. With the 5-volt source, to get 40 milliamps of current, we need a total resistance of about 125 ohms. Keep in mind that the total resistance is always less than the smallest resistor value present, so our third resistor will need to be more than 125. After a short guesstimating session, I found that using 2 470 ohm and 1 220 ohm resistor will give me a total resistance of about 110, which is close enough. I can put the circuit together and show that the voltage across each is 5 volts, but the 40 milliamps of current has been divided among them proportionally. If you build a circuit that is a combination of both parallel and series resistors, Figuring out what voltages are present, as well as what currents are passing through which resistor, isn't as difficult as you might think. Let's use this circuit as an example. We have 3 individual resistors in series, with 2 groups between them that are in parallel. First, we want to figure out what the total current passing through the whole circuit is. To do this, we take these 2 parallel groups, calculate their total resistance, and treat them as if they were one single resistor. Resistors in series simply add together, so we add up these 5 resistor values, and from there we can calculate the total current that a circuit is drawing. Also, we can use the proportional value of each resistor to the total resistance to find out the individual voltage drop present across each of the 5 resistances. Keep in mind that these values should add up to the voltage source. The amount of current passing through each section of the circuit is the same, but at the parallel parts, the current splits between the different paths. To figure out how much current is going through each resistor, we can use Ohm's law based on the resistance value and the voltage drop of that particular resistor. Once we know how much voltage and current each resistor is dealing with, we can calculate the wattage each resistor is experiencing to make sure we aren't exceeding any of their rated wattage tolerances. And that's pretty much all you need to know about resistors to start playing around with electronics. The last thing I want to cover in this video is just that there are many different types of resistors out there, and they have pros and cons when used in different applications. If you're just trying to tinker around and not planning on building some high-performance audio system or something like that, you really don't need anything more than a box of cheap carbon film resistors. You can typically buy a box of 1,000 for about $10. Someday, if you're trying to build something and you care about getting the best quality prototype you can make, it might be worth doing research into what type of resistor would be best for your project, but that's really not necessary when you're just starting out. I understand it can be daunting not really knowing what to order when there's so many options out there, and not only can the cost of specialized equipment be expensive, but the cost of a bunch of small things adds together quickly as well. What I would recommend is finding a starter kit online that comes with a collection of resistors, capacitors, and various things packaged into it to make things easy on you. As you get started and play around, you can order more specific things once you get bigger and better ideas on what you want to make. I would look for a kit that comes with an Arduino Uno, a breadboard, components like resistors, LEDs, and capacitors, as well as a collection of other fun things like sensors, motors, buttons, and more. I'm not going to shout out a specific kit or bundle because I don't want to recommend something that I can't vouch for the quality of, but years ago I bought this beginner's book on Arduino and I thoroughly enjoyed it. You can expect to spend between $75 to $150 on a book and starter kit, but I think it's well worth it. If you're like me and you enjoy building things, this is a very fun and rewarding hobby. Thanks for watching.